Hi everyone, this video is to go over page 3 of Midterm 2 for Chem 3A at UC Berkeley in fall 2019, taught by MaryAnn Robak. So here we go. So we are now on question 3B, it's the first question on page 3, and it says that the mechanism is an acid-base step followed by an intramolecular, meaning that it's going to be the nucleophile and the electrophile are both going to be within the same molecule. SN2 reaction. Add stereochemistry to the product structure. We actually don't need to do that. That was a mistake. It was already given to us. But we do need to draw the curved arrow mechanism. As you can see, like these, the stereochemistry for the final product was already shown, so we don't need to worry about that part of the question. But we do need to show the mechanism. And so it says, start by redrawing the reactants using the R abbreviation defined above. So it gave us this little circle right here, and it defined it as R in our reactant X. So we're just going to redraw that. So we start with R, and then that's connected to the carbon, another carbon, the OH group, and then this OS, double bond O, CH3. Okay, so it says that the mechanism is going to start with an acid-base step, followed by intermolecular SN2. So the first step is going to be acid-base. This alcohol right here can act as an acid. So let's actually redraw it where we show the bond for the alcohol, because we know we're going to have acid-base. And then NaOH is really Na plus and OH minus. So you can just use that OH from the sodium hydroxide. We can use that to attack this hydrogen, and the electrons between the oxygen and the hydrogen will go to the oxygen. Note that this is not necessarily a favorable or unfavorable acid base, because we're going from ROH to ROH. So those are very similar acids. For the conjugate acid is water, which is also just like the ROH, and the acid in the first place is an alcohol, which is an ROH. So overall, this isn't necessarily like favorable or unfavorable, it's just what we have to do for this reaction. So then we get, let's copy it down. We have O negative, and then this H3, and we have water. And then it says that there's an intramolecular SN2 reaction, and we can see that in the final product we have this leaving group, and we see that we also have, we can look here, we see that this is the same R group in our starting material in X. That lets us know that this oxygen is going to attack this carbon right here, so that it forms that 3 cycle that's right here. That's what will be formed here. And at the same time, this is the leaving group that's going to leave. Since we know it's SN2, that means it's happening in one step. The leaving group leaves, and the nucleophile attacks the electrophile, where this site right here is the electrophile. Let's just label that so that we know. Electrophile. And this oxygen here is the nucleophile. And this whole thing, let's see, purple. This is the leaving group. Oh, that's kind of too dark. This is the leaving group. Water is just another side product. You can see it ends up right there. And the Na plus is from the sodium hydroxide, because we don't use the sodium plus. So let's see. So in SN2, the stereochemistry is inverted. And so let's pretend that we don't have the stereochemistry given to us because we want to be able to figure out the stereochemistry. That was actually part of the question. It was just a mistake that we weren't actually asked it. And so when it attacks, so we have this R group here, and then at the same time that this wedge group is leaving, this oxygen is going to attack from the opposite side. And so what we can do is we can show, we can either replace where the leaving group was with that oxygen, but since we drew our curved arrow this way, let's put it on the other side. Oh. So let's attack from this side, and that means that we're going to keep the stereochemistry. So the oxygen is going to attack from the top, where the leaving group was leaving before, from the other side. And then the oxygen is still connected to that carbon, and then that carbon, so like that. Okay, and then you see that in the final product, it's where the oxygen is face down. And so if we rotate this is just a rotation around this bond. We can just like imagine like twisting this entire thing so that it's so the oxygen is down here, and then this twists around and this twists around. It's all just like basically twisting around this line. Then it'll be it'll now be wedged down to the oxygen and like that, which is exactly what Y is, you can see, because this R group is still the same with the dashes there, and now we see that we get the same stereochemistry that we should have gotten. Okay, let's see. So it says, finish drawing the reaction coordinate diagram for reaction B for step C. That's what we're on now. The starting material and product energies are given. Take into account the KEQ of the acid-base step and the relative rates of the steps. Okay, so acid-base is pretty quick compared to SN2. SN2 is going to be kind of slow because the leaving group and the starting material are both attacking at the same, or sorry, the leaving group is leaving at the same time that the nucleophile is attacking the electrophile, so it all needs to happen simultaneously. There isn't like a slow step and then a fast step, there's just one step, and so that's going to be slower than the acid base, so that means that there's going to be less of a, or there's going to be more of a jump for the SN2 than there is for the acid base, and like we were saying before, the acid base isn't really favorable or unfavorable, it's about equal. And so this is going to be our middle step. We're going to have a middle step here, so let's move that right here. And it's going to be on the same energy level because the acid and the conjugate acid have similar pKa's. Like we were saying before, this is an ROH for the acid right here. And then the new acid is water. Let's pick a different highlight color. So ROH and water are both of the form ROH. One of them is an alcohol, one of them is water. And so they're going to have similar pKa's. And, I see, okay. So this is saying the original materials are X and NaOH. The middle materials are going to be, it's going to be X negative. That's just what I'm going to write. Because it's basically the same thing as X, but without one of the hydrogens. And it's going to be, yeah, it's just that. X negative. I guess we could write out the whole thing like they did here, but without the H. But, yeah, it's just going to be X negative. And it takes some energy to go from X to X negative. Oh, I guess we can write water too. It takes some energy to go from X to X negative. But at the end, they're going to be at the same energy level. If that makes sense. It's going to take some energy to get the reaction to happen, but it's not really favorable or unfavorable, so it just takes a little bit of energy, and then it'll happen, and it can go back and forth. They're pretty equal in stability, the alcohol and the water. And then it's going to take significantly more energy. Oh, that's kind of ugly. It's going to take more energy, which is why we're going higher up, to get to step Y. Okay. Hopefully that makes sense. Okay. So the next question is saying that if there is no sodium hydroxide as as one of the starting materials, what will happen instead as SN2, and explain why it is so much slower than mechanism B. So we're going to start by redrawing the X material using the R abbreviation. So that's just what we had right up here. We're just going to recopy that over here. So that's R O S H3 and then OH. Okay? And it says that we're just going to do an SN2 reaction without using any sodium hydroxide. So instead of having the hydroxide group up here, that's too late. Sorry. Instead of having that deprotonate the hydrogen here, we're just going to have the oxygen attack the site at the same time that the leaving group leaves. So that's not as good of a nucleophile, right? It's OH, or it's an oxygen that doesn't have a lone pair to spare. It just has its normal lone pair, one of its two normal lone pairs. So it can act as a nucleophile. It's just not as strong of a nucleophile as it would be if it was an O negative. But we're gonna show it anyway. Let's erase that hydrogen. So this is what the SN2 would look like without the acid base step first. We would attack there, the leaving group would leave, and we'd get R, and then we can just show that down there, OH, triangle, the carbon, that's this carbon right there, and then we'd also, so the O would be a plus, yeah, that would be a plus charge, and then we'd have O, S, double bond O, C, H3, and that'd be a negative charge. So why is this mechanism so much slower and it doesn't occur compared to mechanism B? It's because we have a much worse nucleophile now. Mechanism C has a worse nucleophile. Alright, because oxygen with just a 0 formal charge is a much worse nucleophile than oxygen with a negative charge. Okay, so last problem. A possible undesired reaction that can compete with reaction B would involve only an SN2 reaction step using hydroxide as a nucleophile. So instead of doing the acid base with the hydroxide, we would use OH as a nucleophile and just do an SN2 with material or molecule X. And so draw the products of this reaction and explain whether it would be more or less thermodynamically favorable than reaction B. So I remember that during the test I was like, oh, obviously it would be less favorable because it said it's an undesired reaction. But that's not what it means. It means that like we're trying to do mechanism B, but this is another thing that could happen, and we need to determine whether or not this is actually more likely to happen than mechanism B, which would mean it's more favorable, or if it's less likely to happen than reaction B, which would mean it's less favorable. Or it could be about the same too. And so if we are to take material X, which you'll recall is, let's just redraw it. So it's R, wedge line, O, S, O, O, C, H3, and then this and this, OH. And we're saying that we're going to do SN2 with the OH group instead of acid base. Then that means that we're still going to have the same leaving group right here. And we're going to have the sodium plus, and we're just going to have the OH negative go and attack this carbon at the same time as the leaving group leaves. And so it'll attack from the underside, and it will be like this. Okay, actually I don't like the way I wrote that. OH. Okay, and it says, predict whether it would be more or less thermodynamically favorable than reaction B. So, the nucleophiles are about the same, right? Because this is like an OH negative, and then reaction B is also like an O negative kind of thing. Like they're both O negatives as the nucleophiles. The electrophiles are in the exact same spot. So those are both the same. The only thing that's different is that our ending material isn't in the three-membered ring, which is actually super favorable that we're not in the three-membered ring now, because like I've said in another video for I think exam 1, a three-membered ring has a lot of ring strain. Tetrahedrals want to be about 110 degrees apart between bonds, and if you're in a three-membered ring, that's 60 degrees, right? It's an equilateral triangle, so it's going to be 60 degrees apart instead of like 110. That's like half of it, so there's a lot of strain on those bonds. And so reaction D is actually going to be more favorable than reaction B because there isn't ring strain in the product. Right, the rest of the reaction is about the same. The nucleophile strength, the electrophile strength, those are both the same, approximately, but the final material is a lot more strained. And that's also, again, a reason why it took so much energy to get to the final material, because it is strained to have that ring at the end, the three-membered ring. Okay, so we are halfway done with midterm 2. Thank you for watching.